To understand impedance and improve troubleshooting skills, several resources can be beneficial. Firstly, consider books such as Electric Circuit Analysis: A Practical Approach by Roger Tuckheim, Troubleshooting Electrical Systems by Christopher Hart, Fundamentals of Electric Circuits by Charles Alexander and Matthew Satiku, AC Circuit Analysis by Javad Hashemi, and The Art of Electronics by Paul Horowitz and Winfield Hill, specifically Volume 1, Chapter 6. When selecting resources, look for clear explanations of impedance, focusing on its calculation and its impact on circuits. Secondly, ensure there are examples and exercises provided that are designed to reinforce understanding. Thirdly, consider the availability of practical troubleshooting scenarios and techniques which help in real-world applications. Fourthly, check for coverage of alternating current, AC circuits, and impedance matching. To effectively use these books, firstly begin with the basics of impedance and alternating current, AC circuits. Secondly, work through the examples and exercises, which can help test your understanding. Thirdly, apply the concepts to real-world troubleshooting situations. Fourthly, refer back to the books as needed for clarification or refreshers. To supplement this knowledge, consider other online resources. Firstly, explore tutorials such as the one on impedance in AC circuits available at electronics-ws/circuits/impedance.html. Secondly, look into resources on troubleshooting electrical systems like those found at electricafery.com/troubleshooting-electrical-systems/. Also, consider online courses such as Electric Circuits 1 on Coursera, available at coursera.org/learn/electric-circuits-1, and AC Circuit Analysis on edX, available at edX.org/course/AC-circuit-analysis-0. Impedance is the measure of opposition that an electrical circuit presents to the flow of alternating current, AC. It extends the concept of resistance to AC circuits, taking into account not only the resistance but also the effects of capacitance and inductance. Impedance is typically represented by the symbol Z and is measured in ohms. It is a complex quantity composed of two parts: resistance, R, and reactance, X. Resistance, R, is the opposition to current flow due to the material's properties and is the real part of impedance. Reactance, X, is the opposition to current flow due to capacitance and inductance, and it is the imaginary part of impedance. Capacitive reactance, X_C, decreases with increasing frequency and capacitance, while inductive reactance, X_L, increases with increasing frequency and inductance. The formula for impedance is Z equals R plus JX, where J is the imaginary unit. The magnitude of impedance, also known as the absolute value of impedance, is calculated as the square root of R squared plus X squared. This value represents the total opposition to current flow in the AC circuit. Understanding impedance is crucial for analyzing AC circuits because it affects the current-voltage relationship. Ohm's law for AC circuits is V equals I times C, where V is voltage, I is current, and Z is impedance. This relationship is essential for determining circuit behavior, calculating power, and designing filters. Impedance matching is the process of designing a circuit so that the impedance of the source equals the impedance of the load. This is important because it maximizes power transfer. When the impedances are not matched, some of the power is reflected back to the source, reducing the efficiency of the circuit. Impedance matching is often achieved using transformers, which can change the impedance level of a circuit. In practice, impedance is used in many applications. For example, in audio systems, impedance matching ensures that the amplifier can efficiently drive the speakers. In radio frequency (RF) circuits, impedance matching is critical for transmitting signals with minimal loss. In power systems, impedance is used to analyze and protect the grid from faults. Troubleshooting electrical systems involves identifying and resolving issues that prevent the system from functioning correctly. This often requires a systematic approach, including understanding the system's design, using appropriate test equipment, and applying problem-solving skills. Firstly, understand the system. This involves reviewing the system's documentation, including schematics, wiring diagrams, and operating manuals. It is important to know how the system is supposed to work before attempting to troubleshoot it. Secondly, gather information. This involves collecting data about the problem, such as when it occurs, what symptoms are present, and what steps have already been taken to address it. This information can help narrow down the possible causes of the problem. Thirdly, isolate the problem. This involves using test equipment to measure voltages, currents, and resistances at various points in the system. The goal is to identify the specific component or circuit that is causing the problem. Fourthly, repair or replace the faulty component or circuit. This may involve soldering, replacing a circuit board, or rewiring connections. Fifthly, test the system after making repairs. This ensures that the problem has been resolved and that the system is functioning correctly. There are several tools and equipment commonly used in troubleshooting electrical systems. Firstly, a multimeter is used to measure voltage, current, and resistance. Secondly, an oscilloscope is used to visualize electrical signals and identify waveform abnormalities. Thirdly, a circuit tracer is used to locate specific wires or cables in a complex wiring system. Fourthly, a thermal imager is used to detect hotspots or overheating components. Fifthly, a power quality analyzer is used to measure and analyze power quality parameters such as voltage, current, harmonics, and power factor. When troubleshooting electrical systems, it is important to follow safety precautions. Firstly, always energize the circuit before working on it. Secondly, use appropriate personal protective equipment (PPE) such as gloves and safety glasses. Thirdly, follow lockout-tagout (LOTO) procedures to prevent accidental energization of the circuit. Fourthly, be aware of potential hazards such as arc flash and electric shock. Troubleshooting electrical systems often requires a logical and systematic approach. Firstly, start by checking the basics such as power supply, fuses, and circuit breakers. Secondly, use a process of elimination to narrow down the possible causes of the problem. Thirdly, use a divide and conquer strategy to isolate the faulty component or circuit. Fourthly, consult with other technicians or experts if needed. Consider a scenario where a motor is not starting. Firstly, verify that the power supply is present and that the circuit breaker is not tripped. Secondly, check the motor windings for continuity and insulation resistance. Thirdly, inspect the motor starter and control circuit for proper operation. Fourthly, if the motor is still not starting, consider the possibility of a mechanical issue such as a locked rotor or a faulty bearing. Now consider a scenario where a lighting system is flickering. Firstly, check the voltage of the light fixture to ensure that it is within the specified range. Secondly, inspect the wiring connections for loose or corroded terminals. Thirdly, check the ballast or driver for proper operation. Fourthly, if the flickering persists, consider the possibility of electromagnetic interference, EMI, or a faulty light fixture. Another consideration is harmonics in electrical systems, which are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency. Harmonics can cause a variety of problems, including overheating of equipment, misoperation of protective devices, and reduced power factor. Troubleshooting harmonic problems often involves using a power quality analyzer to measure the harmonic content of the voltage and current waveforms. Solutions to harmonic problems may include installing harmonic filters, using harmonic mitigating transformers, or redesigning the electrical system. Another factor is grounding, which is an essential safety measure in electrical systems. Proper grounding provides a low impedance path for fault currents to flow back to the source, which helps to protect equipment and personnel from electric shock. Troubleshooting grounding problems often involves using a ground resistance tester to measure the resistance of the grounding system. Solutions to grounding problems may include installing additional ground rods, improving grounding connections, or redesigning the grounding system. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is reactive and is not contributing to useful work. Low power factor can result in increased energy costs, reduced system capacity, and voltage drops. Troubleshooting power factor problems often involves using a power quality analyzer to measure the power factor. Solutions to power factor problems may include installing power factor correction capacitors, using synchronous motors, or redesigning the electrical system. In summary, understanding impedance and mastering troubleshooting techniques are critical skills for anyone working with electrical systems. These skills require a combination of theoretical knowledge, practical experience, and a systematic approach to problem solving. Regular study, application, and continuous learning are essential for improving electrical skills and ensuring the safe and reliable operation of electrical systems.